Okay, we are at chapter 17, superposition and standing waves. Let's go ahead and share the uh, PowerPoint, and it starts off with a picture of Jack White. I had to ask my daughter who Jack White was, and she says he plays with the white stripes. I didn't know that. Uh, so, and the story is talking about you playing around with the guitar, and you notice that if you move your hand and press press down at different locations, you can change the tone of the guitar, and we'll learn about that later on. But that's just kind of the intro story, and let's get right to the superposition principle. If two or more traveling waves are moving through a medium, the resultant value of the wave function at any point where the waves both exist is the algebraic sum of the values of the wave functions of the individual waves at that point. So what is that saying? That's saying that if you're listening to, let's say, an acoustic band, we'll take out the microphone and um, uh, the microphones and the electronics associated. If you're just listening, like let's say the two guitarists, you don't get like one set of waves from one guitar and another set of waves from a voice and another set of waves from the second guitar and another set of waves uh, from the other voice. They all kind of blend, and you get an algebraic sum of all those waveforms hitting your ears. So it's not. If you recall, we talked about the compression and rarefaction of air molecules to create sound. Well, these compression and rarefaction, they all kind of superimpose. So you're not getting different sets of waves. You're getting like one wave that has an algebraic sum of all these wave patterns. Um, okay, so here is, why is it blank? Okay, here is an example of superposition. You have two waves, y1 and y2. Obviously, y2 is greater than y1. When the pulses overlap, the wave function is the sum of the individual wave functions. So you can see in B, it's y1 plus y2. Uh, that's where they're just starting to meet. And then when the crest of the two pulses align, the amplitude is the sum of the individual amplitudes. Again, y1 plus y2. When the pulses no longer overlap, they have not been permanently affected by the interference. In other words, they will go through and they will continue uh, on to the other side. So the waves have a life of their own, and they won't be interrupted by an interfering wave. Okay, now we see um, two different waves, one going positive and one going negative. When the pulses overlap, the wave function is the sum of the individual wave functions. When the crests of the two pulses align, the amplitude is the difference between the individual amplitudes. That's why the y1 is reduced, because the y2 is, we'll call it negative. It's really kind of a trough. And when the pulses no longer overlap, they have not been permanently affected by the interference. So the waves, again, have a kind of a life of their own. They won't be affected by interference from other waves. Okay, two pulses move in opposite directions. Um, on the two pulses move in opposite directions on the string, and are identical in shape and size, except that one has positive displacements of the elements of the string and the other has negative displacements. At the moment the two pulses completely overlap on the string, what happens? Um, the energy associated with the pulse has disappeared. The string is not moving. The string forms a straight line. The pulses have vanished and will not reappear. Well, the only one of those that is true is C. The string forms a straight line because it's y1 plus y2. Um, so let's look at, continue this superposition of sinusoidal waves. A sound wave from the speaker S propagates into the tube and splits into two parts at point P. The two waves, which combine at the opposite side, are detected at the receiver. The receiver happens to be your ear. And I actually do an experiment, and I'll probably post as a separate, on a separate page, I'll post the experiment, and just for you to observe the interference of uh, the interference when you lengthen R2 in this case. So let's look at the calculations. Oops. Okay, we have two different waveforms. If you recall, we studied the expressions for the wave. Y1 equals A sine kx minus omega t, where k is equal to 2 pi over lambda. It's called the wave number. It's how many waves, how many radians are in 1 meter of length. The higher the frequency, the more radians you get per meter. So the wave number goes up with frequency. Minus omega t, omega is 2 pi times the frequency, omega t. So the y1 is a sine kx minus omega t. Y2 is equal to a sine kx minus omega t plus some phase angle phi. So the addition of y equals, the addition y is equal to y1 plus y2. So we just, using the distributive property, the a comes out and we have sine kx minus omega t plus sine kx minus omega t plus phi. And we use an identity, sine a plus sine b equals 2 cosine a minus b over 2, sine of a plus b over 2. And using, let's see, if we let a equal kx minus omega t, and b equals kx minus omega t plus phi, then we get this particular equation, y equals 2a cosine phi over 2 sine kx minus omega t plus phi over 2. So that comes from the a minus b and the a plus b. We get those that equation. Now this lets us know that the resultant wave function is sinusoidal and has some frequency and wavelength as the individual has the same frequency and wavelength as the individual waves. The resultant wave function, the sine function, incorporates the same values of k and omega that appear in the original waveforms. The amplitude of the resultant wave is 2a cosine phi over 2, and the phase constant is phi over 2. Now, so the delta R is R2 minus R1 n times lambda, where n is equal to 1, 2, and 3. These are the path lengths. If we go back, let's see, does it show it on the, if we go back, you'll see that the R is equal to the path length. You see the little red dot on the bottom is R path length R1, and the dotted line on the top is path length R2. So that's where the delta R is R2 minus R1, and it's equal to n lambda, where n is equal to 0, 1, 2, 3. When these things are in phase, you can see that the peaks are aligned and the troughs are aligned. This is when the individual waves are in phase, and therefore they're indistinguishable. You have constructive interference. The amplitudes add. You can see I think the two blues are the Y1 and Y2, and the Y is the resultant. Cosine phi over 2 is equal to plus or minus 1, and phi is equal to 0, 2 pi, 4 pi, and so on. Now, what if the individual waves are 180 degrees out of phase? Then you have destructive interference, and the waves cancel. And this is where cosine phi over 2 is equal to 0, and that is at phi equals pi, 3 pi, 5 pi, and so on. and R is equal to lambda over 2, 3 lambda over 2, and n lambda over 2 for n odd. Now, I think what we're going to do, we're just going to have lambda over 2 where we get the interference, and we'll be able to see that on the video. Okay, so when it's intermediate intermediate values where the phase angle varies, then you get a superposition, and you get the Y is shown. The intermediate result is neither constructive nor destructive. You just get this this pattern that's just the algebraic sum. So now we get to the end of this section. We have the analysis model, waves and interference. You have constructive interference. You have destructive interference. The red line or brownish line in either case is the sum, and you can see it's greater than both of them in the constructive interference, and in the lower one it's destructive, so it's lower than the greatest one at least. And these can be used. A piano tuner listens to a piano string and a tuning fork vibrating together and notice beats. You get we'll learn about beat frequencies later. Light waves from two coherent sources combine to form an interference pattern on a screen. A thin film of oil on top of water shows swirls of color because of and you'll learn next semester about the refraction, and the refraction breaks up the waveform. And the X-rays passing through a crystalline solid combine to form a lava pattern. Okay, and that's it for this one. We'll go on to standing waves in the next lecture.